In this class number 5 of our automotive air conditioning course, we are going to study expansion devices in greater depth and with much more detail. Let's begin by saying that expansion devices are fundamental components in automotive air conditioning systems, responsible for obtaining and regulating the system's low pressure in a controlled manner, and also for accurately metering the refrigerant flow that enters the evaporator at all times. Their proper operation directly impacts the cooling level inside the cabin, the energy efficiency of the system, the compressor's service life, operational stability, and correct performance under different climatic conditions and thermal loads. In the automotive sector, 3 main designs or types of expansion valves predominate. Fixed orifice tube, a non-metering design, simple in construction, and widely used in traditional systems due to its low cost and ease of replacement. Thermostatic expansion valve with sensing bulb, bulb type TXV, which regulates based on the actual temperature at the evaporator outlet, offering much more precise control of refrigerant flow. Block type expansion valve, H-block, compact and widely used in modern vehicles due to its integrated design and high accuracy in refrigerant flow control based on temperature. Before continuing, remember that in the description of this video, you will find the link to access more information and the knowledge test corresponding to this class. 1. Fixed orifice tube. It does not have any internal mechanism, as it cannot regulate refrigerant flow dynamically by itself. It basically contains a small, calibrated orifice inside, whose size depends on the external color of the calibrated orifice tube, meaning it does not actively modulate flow and always operates under the same mechanical restriction, regardless of the system's thermal load or ambient operating conditions. Main characteristics: A. Economical and very reliable, because its simple construction minimizes failure points, reduces the number of internal components, and greatly simplifies diagnosis and replacement if necessary. B. It is used in systems that include an accumulator with a filter dryer located just before the compressor. This accumulator can store excess liquid refrigerant, preventing liquid refrigerant from reaching the compressor's suction line, since the calibrated orifice tube cannot regulate flow and always operates with a fixed restriction. C. Since it has no internal mechanism, there is no possibility of mechanical damage, only potential obstruction due to internal system contamination, which simplifies failure analysis. Disadvantages: A. It does not control refrigerant flow. Therefore, it cannot accelerate cooling or reduce it either, meaning systems with a calibrated orifice tube behave less precisely compared to more advanced expansion devices that do respond to the vehicle's real thermal demand. B. Higher probability of evaporator freeze-up under low load conditions, especially in cold climates or during long trips with low thermal demand. That is why systems with a calibrated orifice tube include a low-pressure switch to turn off the system when cooling is excessive and there is risk of evaporator icing. C. Susceptible to obstructions by dirt or particles from the compressor, which can severely affect flow, reduce cooling capacity, increase system pressures, and significantly reduce the overall performance of the air conditioning system. Before continuing, remember again that in the description of this video, you will find the link to access more information and the knowledge test corresponding to this class. 2. Thermostatic expansion valve with sensing bulb, TXV. This type of valve regulates refrigerant flow by using the temperature measured at the evaporator outlet through a highly sensitive sensing bulb. This bulb actuates a mechanism that commands the diaphragm of the valve. For example, when the sensing bulb located on the evaporator outlet pipe detects a temperature higher than normal, the substance inside the bulb expands and moves the internal diaphragm of the valve, opening or regulating the refrigerant passage to allow greater cooling capacity. Now, when the sensing bulb located on the evaporator outlet pipe detects a temperature lower than normal, the substance inside the bulb contracts and moves the internal diaphragm of the valve, closing or restricting the refrigerant passage to avoid excessive cooling that could affect comfort or cause freezing. Advantages. A. Excellent thermal control, allowing for more consistent temperatures inside the vehicle cabin and greatly improving passenger comfort. B. Higher efficiency than the fixed orifice cube by adjusting refrigerant flow based on the system's real demand, resulting in better use of refrigerant and compressor work. C. More stable in response to changes in thermal load, such as variations in outdoor temperature or in the speed of the interior blower, adapting in real time to operating conditions. Disadvantages. A. Sensitive to vibrations, dirt, or installation errors, which can affect accuracy and cause unexpected variations in refrigerant flow and negatively affect overall system performance. 3. Block-type expansion valve, H-block. The block-type thermostatic expansion valve works identically to the bulb-type expansion valve previously explained, being a compact variant widely used in modern vehicles. Its fundamental difference is that the sensing bulb is not located externally on the evaporator outlet tube. Instead, the outlet tube returns to the block valve so that the internally located sensing bulb measures the refrigerant temperature directly. Due to its ease of installation directly onto the evaporator tubes and its robust, efficient, and compact design, this type of valve is widely used in many modern vehicle models. Operation. It automatically controls superheat, which corresponds to the difference between the inlet temperature and the outlet temperature of the evaporator, ensuring that only superheated vapor reaches the compressor and preventing liquid refrigerant from carrying over. Most block-type valves are factory set to maintain a difference of approximately 5 degrees Celsius, or about 9 degrees Fahrenheit, between the refrigerant entering and the refrigerant leaving the evaporator, an optimal value for compressor protection and system energy efficiency. Practical example of operation. On a hot day, or with several passengers inside the vehicle, the gas temperature at the evaporator outlet may be high due to the large thermal load produced by environmental conditions and internal heat. In this case, the valve interprets that more refrigerant is needed to improve cooling and opens further to increase refrigerant flow, allowing greater heat transfer and achieving higher cooling capacity. On a cold day or under low thermal load conditions, less refrigerant is required, so the valve partially closes to reduce flow, avoiding overfeeding and reducing the risk of freeze-up. This dynamic control optimizes the system's efficiency, prevents evaporator icing, maintains stable operating pressures, and protects the compressor from damage caused by improper operating conditions. Common expansion valve failures. A. Intermittent or insufficient cooling. The valve may remain stuck in a partially open or partially closed position, causing inconsistent cooling during long trips or sudden changes in outdoor temperature, directly affecting thermal comfort. B. Abnormal pressures, high discharge, and low suction. A blocked valve, or one that does not open properly, causes low suction pressure and high discharge pressure, increasing compressor load, raising energy consumption, and significantly reducing system efficiency. C. Frost or ice on the evaporator. If the valve allows too much refrigerant through, the evaporator may become excessively cold, causing ice formation that obstructs airflow, reduces cooling capacity, and affects vehicle comfort. D. Unusual noises, whistling or knocking. Irregular refrigerant flow due to faulty valve opening may produce noises inside the system that indicate improper operation and possible internal damage. E. Short cycling of the compressor. Incorrect refrigerant flow can cause the compressor to turn on and off repeatedly, reducing its lifespan, increasing mechanical wear, and generating unnecessary vibrations that affect system operation.